let's discuss a specific type of event called a collision. A collision is where two objects come together and interact for a brief period of time, changing their velocities, exerting some force on each other, changing their kinetic energies, and afterwards flying away, possibly in different directions. Every physicist has a soft spot in their heart for collisions, because collisions are the main way that we know anything about anything subatomic. The parts of the atom, protons, neutrons, electrons, you've probably heard about them for a while, but we wouldn't have any idea what those were or anything else smaller than them if it weren't for the study of collisions between those particles. When we start to analyze a collision, we think of it in terms of a before situation, a collision time, and an afterwards situation. It usually helps to draw a diagram of those situations. Here's what a before situation might look like. In a collision, we always have two objects. Their masses are considered known, usually, and they have some initial velocities, which are also usually considered to be known. We set up the particles, we know about them, we send them in on a collision course. During a collision, the particles interact with each other. This happens over a very short length scale. They get close together, and over a very short time scale. The collision is like, boom, they hit each other and then they are done. We don't want to require specific information about this collision period because that depends on the details of the forces and it can be rather complicated. However, in a good collision, we always have the same two particles coming out afterwards. No disintegrations. So after the collision, we have the same two objects with the same two masses. There's no disintegrations or conglomerations. And they have final velocities, v1f and v2f, which are, in general, different from what they came in with. So even though we don't know the details of the collision process in the middle, we still can be guaranteed that the momentum is conserved between the before situation and the after situation. In the most general form, we would write P0 for the initial total momentum as m1 v10 plus m2 v20. And the final momentum, P sub f, as m1 v1f plus m2 v2f. Conservation of momentum, the absence of external forces, is virtually guaranteed for a collision since it happened on such a short time scale. But the equation is that the initial momentum P0 and the final momentum are equal to each other. Notice that momentum doesn't tell us everything about the collision. It only relates the before to the after, and it only gives us one equation. If we have a collision in one dimension, then this gives us one equation. In 2 dimensions, it gives us 2 equations, and in 3 dimensions, it gives us 3 equations. So there is one equation from conservation of momentum for each dimension of the vectors. Generally, we consider the masses to be known and the velocities incoming to be known, and we want to find out the velocities of the outgoing objects. Notice that the number of velocities is 1, 2. And so the number of unknown variables is equal to twice the number of dimensions in the velocity vector. If we do a collision in one dimension, there is 1, 2 unknowns, but only one equation. If we do a collision in 2 dimensions, there are 2, 4 unknowns, but only 2 equations. So we can't solve exactly using the conservation of momentum. we need to have some other principle that can describe the collision for us and allow us to get a exact, unique solution. We'll now give two specific types of collisions, two approximations to real collisions, that give us the additional information that allows us to solve for the final outgoing velocities. The first of those is called an inelastic collision. The defining feature of an inelastic collision is that the two objects come together and stick. After the collision, they move off with the same velocity. So our before and after diagrams would look like M1 comes in with V1 0. M2 comes in with V2 0. We have some collision between them, and as a result of that collision, they're somewhat stuck together. So M1 and M2 move off. They have the same final velocity. So we only use really one variable for that, Vf. But it's the same as V1f and V2f. All of these velocities are the same. The objects are stuck together. So for our conservation of momentum equation, with the initial momentum on the left, the final momentum on the right can be written as the total mass, m1 plus m2, times their common velocity vector, vf. This allows us to solve easily for vf by dividing both sides of the equation by the total mass. To interpret this value, we can look at it as a weighted average. Mass 1 weights velocity 1, 0, the initial velocity of object 1, and mass 2 weights velocity 2, 0, the initial velocity of object 2, and dividing by the total makes it an even weighting. So conceptually, what we find out is the final velocity is more or less an average somewhere between the velocity of mass 1 and the velocity of mass 2, with more weight given towards the mass that's heavier. Let's do an example with some numbers in one dimension. I'll set up a situation where a 2 kilogram mass is moving to the right at 40 meters per second. And is about to collide with a 1 kilogram mass that's moving to the left at 2 meters per second. Our momentum and velocity vectors here only have one component, but we still need to take care of if it's a positive or negative sign. The direction is very important. So let's calculate our total momentum here. From mass 1, I get 2 kilograms times 4 meters per second. And from mass 2, I get 1 kilogram times negative 2 meters per second. Negative because it's moving to the left. So the total momentum before the collision is 8 minus 2 is 6 kilograms meters per second. If this is an inelastic collision, which is what we're working on, the final velocity of both objects will be the same. They'll be stuck together. We only have to take our total momentum, 6, divided by the total mass. M1 plus M2 will be 3 kilograms. So we will have 6 kilogram meters per second in the numerator and 3 kilograms in the denominator. So the final velocity of both objects stuck together is 2 meters per second. Since this came out as a positive number, that means it's a velocity to the right. Let's check if that makes sense. We've got 4 meters per second to the left and 2 meters per second to the right, and a velocity somewhere in between those is our expected result. 2 meters per second is between those two, right? -2 and +4 contain the result +2 between them, but it's more heavily weighted towards the one with more mass. So 2 is closer to 4 than 2 is close to -2. In fact, the proportion between them is actually exactly 2/3 of the 4 plus 1/3 of the 2, of the -2. The second type of collision we'll discuss is an elastic collision. The defining feature of an elastic collision is that it conserves kinetic energy. Note that a collision doesn't automatically conserve kinetic energy. The force between the colliding objects has to be purely conservative. Otherwise, some energy might be lost while they stick together. If the force between the objects is conservative and has a potential energy, then it can conserve the total kinetic energy before and after the collision. So we have an additional equation for an elastic collision that the kinetic energy before and the kinetic energy afterwards are the same. We still have conservation of momentum as well, since that's true for every collision. Let's write what these equations look like if we set it up as a one-dimensional collision with two objects. First, I'll write conservation of momentum. Here's momentum before the collision, and here is the momentum afterwards. That's one equation with two variables considered as unknown, the outcoming velocities. Now let's write conservation of kinetic energy. 1/2 mv squared is the general formula for kinetic energy. And when we have multiple objects, we add together their kinetic energies to get the total. So here's the equation that's given to us if we have conservation of kinetic energy also. So we now have two unknowns and two equations. So in principle, there exists a unique solution for the two final velocities if the masses and incoming velocities are known. However, let's be a little more careful. The equation for momentum involves velocities to the first power. It's linear. But the equation for kinetic energy involves the velocities squared. It's quadratic. So if we want to solve for v1f and v2f explicitly, we're going to have to solve a pretty nasty looking quadratic formula. So what I'm going to provide to you now is a technique for solving the elastic collision. It might seem like a little bit of black magic, but I guarantee you that it works and that you can derive it yourself if you follow through my steps. I'll also put this in the notes that I upload to Sakai so that you can see exactly all the steps. The idea behind this method of solving the elastic collision is to look at two related velocities that are not the same as initial or final for either of the masses, but are formed from sums and differences of those. The first one is called the center of mass velocity, VCM. Notice that the center of mass velocity is actually equal to the total momentum divided by the total mass. So it's also the same as the final velocity that would be obtained in an inelastic collision. It sort of represents the average motion of the two-object system. If we know both masses and both incoming velocities, we can immediately calculate the velocity of the center of mass. The second velocity that's related to the velocities of the objects is called the relative velocity. This is the difference between the velocity of object 2 and the velocity of object 1. So if these two objects on their way towards the collision have a relative velocity that's negative, they will eventually hit each other. The distance between them is decreasing. I've written these two quantities as if they were calculated from the velocities before the collision. Before. You can see that they depend only on the initial velocity of mass 1 and the initial velocity of mass 2. The interesting thing that happens is if we take this formula for the kinetic energy here, 1/2 mv squared for mass 1 plus 1/2 mv squared for mass 2, and write that in terms of VCM and VREL instead. When we do that, what we get, after quite a lot of algebra, I'll just give you the answer, is a term in the kinetic energy representing the overall motion of the system. So 1/2 mv squared, except the mass is the total mass and the velocity is the center of mass velocity of the system. The second term here is a term that depends only on the relative velocity. It is also in the form of 1/2 mv squared. The velocity that's squared is the relative velocity, but the mass that's appropriate is somewhat strange. It's the product of m1 and m2 divided by the sum. We can check that this has units of mass, because it would be mass times mass over mass. So it reduces to a mass. This quantity is actually called the reduced mass. And the symbol for it is a Greek lowercase letter mu. It's not really important to know that nomenclature. If you know the two masses of the two objects, you can simply calculate the reduced mass. The point of expressing the kinetic energy in this way is that we can easily tell what's going to happen in an elastic collision. First, let's make a statement about this center of mass velocity. Since the center of mass velocity is essentially the total momentum divided by the total mass, since the total momentum is conserved, the center of mass velocity is not changed by the collision. The average motion of the two particles continues on unaffected. So the center of mass velocity after the elastic collision is the same as the center of mass velocity before the elastic collision. So that means in our term for kinetic energy, this first contribution to the kinetic energy is the same before the collision and after the collision. So that means that the only part of the kinetic energy which could potentially change by the collision is this second term involving the relative motion. In the elastic collision, the kinetic energy before and afterwards must be the same. The first terms were already the same. This coefficient is the same. The only thing that could potentially change is the relative velocity. So our conclusion for the elastic collision is that the relative velocity vector before squared must equal the relative velocity vector afterwards squared. Now, if two vectors have equal squares, that means they must have equal magnitudes, but they can have different directions. So the magnitude of the relative velocity is unchanged in an elastic collision, but the direction of the relative velocity can be changed. In a one-dimensional collision, a direction can only be taken by a positive or negative sign to the velocity. So we have two options. The relative velocity after the collision could be either equal to the relative velocity before or equal to the opposite of the relative velocity before. Let's think about both of those options. If the relative velocity after the collision is equal to the relative velocity before the collision, then nothing has changed in the system. The center of mass velocity is the same, the relative velocity is the same, so the final velocities will be exactly equal to the initial velocities. What's going on there? It appears that we've just gotten a result that says no collision happened. Well, that should be a little bit obvious. If no collision happens, obviously momentum and energy will still be conserved because there was no force at all. So this plus choice here is just giving us a redundancy, repeating the initial conditions back to us. Let's look at the minus choice then. If the relative velocity after the collision is equal to the opposite of the relative velocity before, then the individual velocities will be changed. So that is the situation that gives us the result of the collision. So given that, let's now go back and use these answers to calculate the final velocities of the actual objects after the elastic collision. So if we're given the two masses and the two incoming velocities, we can calculate the center of mass velocity before collision and the center of mass velocity after the collision. Let's treat that as step one. Step two is pretty simple, but we're just going to write it out to realize that the center of mass velocity after the collision will be equal to the center of mass velocity before, and the relative velocity after the collision will be equal to the opposite of the relative velocity before, at least in a one-dimensional collision. We'll call that step two. Now in step three, we use the definitions of center of mass and relative velocity to deduce the final velocities of both objects. When we do that, we will get that v1f, the final velocity of mass 1, is equal to the center of mass velocity after the collision minus a fraction m2 over the total mass multiplied by the relative velocity in the final state. For the final velocity of object 2, we get a similar solution. It's the center of mass velocity after the collision plus a fraction m1 over the total mass times the relative velocity in the final state. So this is an easy way, more or less, to get the final velocities of an elastic collision without having to solve a quadratic equation and deal with square roots or have a much bigger chance of making a calculation error. Now let's work through an example where we have an elastic collision between two objects. Let's start off with a known mass 1 of 3 kilograms moving to the right at 2 meters per second, and a known mass 2 of 1 kilogram moving to the left at 8 meters per second. So we will say that V10 equals plus 2 meters per second, and V20 equals negative 8 meters per second. Our first step is to calculate the center of mass for this colliding system. We'll get 3 times 2 plus 1 times negative 8 for the numerator. And the denominator will be 3 kilograms plus 1 kilogram. So the center of mass velocity is 6 minus 8 in the numerator, negative 2 divided by 4, negative 0.5 meters per second. This makes sense as a value that describes sort of the average motion of this system. For the relative velocity, we just take the difference from V2 to V1. Here we have to be very careful of which object is which and the signs of our velocity vectors. V20 is negative 8 and V10 is positive 2. So for my relative velocity, I get negative 10 meters per second. After the collision, the center of mass velocity will still be negative 0.5 meters per second. The relative velocity between the objects will change from minus 10 to plus 10. Conceptually, this means that the objects were getting closer together at a rate of 10 meters per second before the collision, and now after the collision are flying away from each other at 10 meters per second. Let's plug into the formula now to calculate the actual final velocities of the two objects. There's my center of mass velocity. And I'll subtract a fraction that is m2 over the sum. m2 was 1 kilogram, so I'll have 1 kilogram, and the total was 4 kilograms, so I'll have 1/4 of 10 meters per second. Ten divided by 4 is 2.5, so I have 0.5 minus 2.5. And that means V1F is minus 3 meters per second. For V2F, I'll use the formula here. Negative 0.5 meters per second plus a fraction with m1 in the numerator. That was 3 kilograms or 4 kilograms. Multiplied by the relative velocity afterwards, which is 10 meters per second. Here we have 10 divided by 4, which is 2.5, multiplied by 3, which is 7.5, with minus a 0.5. So the velocity of object 2 after the collision will be 7 meters per second. 7.5 minus 0.5. So it'll be positive 7 meters per second. As we can see, this method keeps the numbers simple all the way along, gives us simple fractions and nice integer or rational answers. We don't have to deal with square roots like we would in a quadratic formula. Now, doing an elastic collision is usually difficult. There's a lot of steps, there's a lot of chance to put the wrong number in the wrong place, or get the signs confused, or just make a math error. And no one is immune to this. I make errors on these problems all the time. The way that I check myself is to plug these results back in to the equations for conservation of energy and conservation of momentum to check if it's correct. Let's do that now and show that we got the right answer. For the initial situation, we already calculated the momentum. It was 3 times 2 for 6, minus 1 times 8 for negative 2. Now let's use our final results to calculate the final momentum explicitly. Mass 1 was 3 kilograms, and after the collision it's moving at minus 3 meters per second. Mass 2 was 1 kilogram, and after the collision it's moving at 7 meters per second. So my final momentum would be negative 9 plus 7. That comes out to minus 2. That's a good evidence that we've got the right numbers, but we also should check conservation of kinetic energy. Before the collision, we've got mass 1 at 3 kilograms, moving at a speed of 2 meters per second. Mass 2 has 1 kilogram of matter and is moving at negative 8 meters per second. So for my kinetic energy before, I've got 3. 2 squared is 4, so 3 times 4 is 12, divided by 2 is 6 joules, according to mass 1. And for mass 2, negative 8 squared is positive 64, times 1 is still 64, divided by 2 is 32. So the total kinetic energy before the collision is 32 plus 6, or 38 joules. Let's check our kinetic energy after the collision as a final test. Now, mass 1 is moving at negative 3 meters per second. And mass 2 is moving at 7 meters per second. Don't forget to square your velocities in the kinetic energy. Let's look at these numbers. Negative 3 squared is 9. Times 3 again is 27. I'll leave the division by 2 at the front for now, saying 27 divided by 2 in joules. For the second term, I have 7 squared is 49, times 1 is still 49, divided by 2. So I have 49 divided by 2 in joules. We've got a common, I left the 2 here so we would have a common denominator. So let's add 27 and 49. The answer will be 60 plus 16, so 76 over 2 joules. And 76 divided by 2 is 38. So we've confirmed that our 2 final velocity answers obey conservation of momentum and conservation of energy. If they do that, they must be the correct unique solution to that elastic collision problem.